Hi, welcome to our talk, Faster Training of Neural ODEs using Gauss-Legendre Quadrature. I'm Alex Norcliffe, and I did this work with Mark Dijzenroth. I'm at the University of Cambridge, and Mark is at UCL, and this work has recently been accepted to TMLR. We start by talking about Neural ODEs, and these are inspired by residual networks, where the hidden representation at a given layer is equal to the previous hidden representation plus a nonlinear function of that. And then when we take a limit of small step sizes, this looks like an Euler discretization of an ordinary differential equation. And this leads to the natural progression of neural ODEs, where instead of discrete jumps, we use a neural network to parameterize the velocity of a hidden state, and then we can input an initial value and then use a black box ODE solver to evolve that hidden state according to the differential equation. Neural ODEs have multiple applications. For example, in time series, where the underlying generating process of the data could be a dynamical system. For example, in this predator-prey cycle, or for example, in generative modeling, where normalizing flows have been taken to a continuous limit in continuous normalizing flows that take advantage of the mathematics in continuous time. So how are neural ODEs trained? Well, they're trained by calculating gradients and then running gradient descent. Now, we can backpropagate directly through the operations taken by a black box ODE solver, which means we can backpropagate through these neural ODEs. However, another method is the adjoint method, which uses a second differential equation solved backwards in time to calculate the gradients. The way it works is we have a state A, and the dynamics are given by dA dt equals minus A df dx. And A at the final time is given by the gradient of the loss with respect to the state at the final time. And then to actually calculate the gradients of the loss with respect to the parameters, we can ODE solve a new state that starts at 0. The initial value is 0 at t1. We solve it to t0, and the dynamics, the velocity is given by minus A, as shown above, df d theta. Now, importantly, this ODE solve can also be looked at as an integral, where we do dl d theta is actually the integral from t0 to t1 of this A df d theta. This was shown in Kidger et al. However, even in that paper, they just used this fact to make the ODE solve faster. However, we would like to use integration methods in this setting, since ODE solve methods might not be as suitable to solve an integration problem as integration methods themselves. We opt to use Gauss-Legendre Quadrature. Gaussian Quadrature is fast to converge, and it works by taking a weighted sum of function values at very specific points along the trajectory. And the reason this can work is because in fact we're solving many one-dimensional integrals in parallel. However, this still requires memory efficiency. A key requirement of the adjoint method over direct backprop is this memory efficiency. Otherwise, direct backprop is just as effective. Previously, Gaussian quadrature has been used in this setting. However, this required dense solutions of these trajectories to run the quadrature, and this had a heavy memory requirement. We instead achieve memory efficiency by choosing how many terms to use before starting the solve, and then we keep a running sum of these of the total during the solve. So that's shown below. We initialize g at 0, and then every time we update g, we add the weight multiplied by a df d theta. So how do we actually choose the number of terms? Because we have to choose these before the backwards solve starts. We make the assumption that a complex forward solve leads to a complex backward solve. This might use too many terms, and it would be slightly slower. However, you would rather use too many terms than not enough. So we can determine the complexity of the forward solve by the number of function evaluations used during that forward solve, the NFE. And then we can use this heuristic, which is the ceiling of some constant multiplied by these number of function evaluations, and then we can scale this by the ratio of the width of the time interval that we're looking at divided by the width of the total time interval. And the ceiling function is used so that we firstly get an integer for n, and so that we round up. C is a constant that we choose, and we found that 1 times 10 to the minus 3 was effective. Now, we can also extend this method to SDEs. We use the Wang-Zakai theorem, which says that we can approximate the solution to an SDE given by dz equals f dt plus g times the Wiener process. And we can actually approximate this with an ODE, where we now have ZO, and we have dZo dt is f plus g times dB dt. Here, f is a smooth approximation to the Wiener process, and as b approaches it, ZO also approaches Z. So the question is, how do we actually approximate dB dt? The Carhoonen-Loeb theorem says that we can approximate it with an infinite Fourier expansion, where the coefficients in front of the cosines here are sampled from a standard normal distribution. And then as capital M increases, then the approximation improves. And we use a truncated sum with approximately 10 terms. And then by training this related ODE, we can then use the Gaussian quadrature method to solve the for the gradients and run gradient descent. And then after training, we transfer the parameters at test time to an SDE solver. So now we can look at the results. So the first test was on these time series where we're doing regression on these sine curves. And we can see that the direct backpropagation method is the fastest, as we might expect. However, following this, the Gaussian quadrature method in blue scales very well with the hidden width, i.e. the number of parameters in the model, whereas the training time scales poorly for the adjoint methods. And then to test if this actually is working and calculating the correct gradients, we plot the test mean squared error as a function of the hidden width, and then we see that ultimately they give the same mean squared errors. So the gradients being calculated do match those calculated by the adjoint method or the direct method. The next test was classification using MNIST, and again we see that Gaussian quadrature roughly stays with the adjoint method for small models, but then as the number of hidden channels increases, it scales better. As the number of parameters increases, this method becomes better compared to the adjoint method. And again, when we plot the test accuracy, we see that the gradients calculated were as effective as those calculated by the adjoint method. Then we tested on a stochastic differential equation. And what we plot here in green is the direct backpropagation, in blue is our Gaussian quadrature method, and in pink is the SDE adjoint method. And so, firstly, on the left, what we see is that the direct method runs out of memory at a hidden width of 50, as we might expect. And so instead, we need to use these memory efficient methods, but we see that the Gaussian quadrature method is faster on the whole than the adjoint method. And then looking at the test KL divergences, we see that they roughly match. The reason they likely don't match is because we trained the ODE approximations rather than the SDE directly with our GQ method. Finally, we look at the memory efficiency of the method. And what we're plotting is the tolerance on the x-axis, i.e. how many function evaluations we might want to use. And then on the y-axis, we actually plot the peak memory usage. And then we see that the direct method increases, but the adjoint and Gaussian quadrature methods stay constant, as we would expect. There's a slight increase in overhead for the Gaussian quadrature. However, the important point is the scaling is constant in this tolerance. So in conclusion, we speed up the adjoint method without regularizing the dynamics and remaining memory efficient. We did this by calculating the solution to the same integral using Gaussian quadrature rather than ODE methods. We extended this to stochastic differential equations using the Wong-Zakai and Calhoun-Loeb theorems, and we tested on various classification and time series regression tasks and found that our method scaled well with a number of parameters. We also determined that the best time to use the method is when we have a small state x but a large number of parameters. We highly encourage you to read the paper for more details. Thank you for listening, and if you'd like to keep in touch, these are our details.